Hello and welcome to lesson 2 of week 10. My name is Mildred. In this lesson, we're going to talk about the binary search tree. The binary search tree is a special kind of tree in which each node has at most two children, a left child and a right child. The left subtree contains only nodes that the key are less than the parent. That is for all of the left child and all of the subtrees for the left, they are all less than the key of the parent. And then for the right, it is greater than the key of the parent, and it doesn't contain duplicate values. Now, because of this structure, search, insertion, and deletion are very fast. Now, the average case, you have big O of log n as the time complexity and big O of n for worst case. And that worst case will only occur when the tree becomes like a linked list. That is, it is sorted and inserted into a simple binary search tree. So to fix things like this, it just means that that tree is not balanced, and we use something we call AVL or red-black tree to balance the tree, and we're going to look at that one in the lesson. Let's look at the operations that we can do on a binary search tree. We can insert, that's add value. We can search, we can traverse through, and when we want to traverse, that means we are visiting all the nodes, and we can do the in order, the left root right. We can do the pre-order, which is root left right, and the post order, which is left right root. And then we can also do the breadth first, which is the level order traversal, also that we use a queue. We can also do delete operations, and there are three cases where we delete a node. When the node has no child, we'll just remove it directly. Where the node has one child, we replace the node with its child, and when the node has two children, we replace with in order successor. So when we delete, these are the different cases we need to handle. So let's implement a binary search tree in Python. The first thing we want to do is to create a class for the node. So let's say class node, and we will create the method, and for this method we want to get the value, and so we'll say self dot, let's get the left and we'll set it to none, and we'll get the right and we'll set it to none. Okay, so the next thing we want to do is to create another class. Let's create a class we call let's call it binary search tree. So I'll create class binary search tree, and I will have an init method for this, and we'll define the root. So we'll say self dot root is equal to, and now we want to create an insert method. We'll do this in two ways. Let's create a private method that will hold all of the core insert functionality, and then a public insert method that will just run the insert. So let's say let me do def. I'll create a private def insert like this, and self current value, right? And I want to say if value is less than, so this is current, sorry, so I want to look at the current value where it is, and if the value is less than the current value, because now we're looking at the parent, anything less goes to the left, anything greater goes to the right. If it's less than current dot value, we want to now look if current dot left, then we'll do a recursive call self dot insert current dot left and then the value. But if not, let's use an else condition. We want to say current dot left, and then we'll create an instance of the node class node and then the value. So now this is for the inner conditional statements. So let's use an else for the outer. And what we want to do at the outer place is to check for the right now. And if it is for the right, we want to do the same thing. So we'll say if current dot right, we want to say self dot insert current dot right value. And then we'll use an else statement here, and we'll say current dot right is equal to node. Now we have done this private method insert that will do all the checks. Let's now do an insert method that will just insert the value here. So let's say def insert. Now we'll have self and takes the value. We will say if not self.root, we want to say self.root is equal to node value, and we just return. Okay, and then now we can say self dot, use the private method insert self.root value. So something like this. So this should work. I think we should have put, well, whichever one comes first. So we want to use this insert method to insert there. If it is not the root, if there's no root, we create a root and then return. But if there is, we want to insert that value. Now let's do the same thing for a method that we can use to search before we try to traverse. So let's say def search, and we want to pass in the value that we want to search. So let's return self.search. So I'm trying to do this exactly as I did that, so we can create this private search that will do all of the checks. So let's do that first before I use that. So let's say def search, okay? And for this we'll get the cell current value. We want to say if not current, we want to return false. And then we want to check if the value we are searching is equal to the current dot value, we want to return true. But if that is not the case, let's use elif because we'll have another condition to check. So elif value is less than current dot value, so we know where we're going to search, because if the value we want to search is less than the current value, we know that we are going to be searching the left side. All right, so we'll return, so we'll do this recursively until we find the value. So we'll say return self dot search current dot left value, and now we use else, we want to search the right. So we'll say return self dot search current dot right value. So now we can use it on this search. So for now, we can now say we'll return the search self.root value. So we can see how we made this private because it's intended to be used just internally with this, until we can always use this method search. We can do traversal, the in order, the pre-order, the post-order. We can build it the same way like we did the rest. I'm going to leave that for you to do and look at your lesson resource to see. Maybe we'll just do the in order traversal here so you can see. We can do it the same way, or you just combine both instead of doing the private and then the method here. So let's do in order. Let's do the private in order, and we want self node and now the result. We want to say node self dot, we're going to recursively call this self in order, and we're looking at the left first, node dot left result, and self dot in order. Let's do the right, then we'll put the parent or the roots at the middle. In order node dot right result, and here we want the root result dot append node dot value. And now we can do the in order here, and we can just return the result if it's present. So we'll say if, or let's just do result is equal to MC, and we'll say self dot in order self dot root result, and then now we return result like this. So we'll stop here and let's test the methods that we've created, and let's look at this class and see if it works. So you can refer to your lesson resource or attend the live web conference, and we'll have a more detailed explanation and look at the other kind of traversal pre-order and the post-order that we have, and then we can look at other methods like the delete method, or a method where we can get like the minimum value that exists in that tree. So let's do the minimum value to be interesting. Let's say def, let's create this mean value. Let's say def mean value like this, and self node, and I want to say while node dot left. So while we're looking at the left node, we'll say the node is equal to node dot left, and then return node dot value. And now the reason we are looking at the left is because we know that for a binary set tree, everything to the left is of lower value than everything to the right, and is still of lower value than the root. So that's why we'll say while the left, and we're just searching only the left side. So let's test this and say if name equal to main, we want to say binary search tree is equal to, we create an instance of the class binary search tree, and we want to supply values. Let's supply it as a list. I'll say 50, 30, 70. I'll have 20, 40, 60. Let's stop here. Now let's loop through this. I'll say for v in the values, we want to insert this, so we'll loop through these values and just insert it into the tree. So we're going to insert v because I created an insert method here for us to insert. So we insert v, and let's print. So we used only in order traversal here, so we'll just use in order. So print in order, and it's going to be bst dot in order. Now we want to let's test this and see. So when we run this, we have for v in value, sorry, it's value not values. So we run again, current dot value, node has no attribute value. I think I made that mistake here. If current dot, if not current, if value equal to current dot value. So let's do the value here. Here we did not initialize the value, so let's say self dot value is equal to value. So you see this mistake, take note of it, because these are the kind of errors you get when things are not initialized properly. So it doesn't know what value is. So I clear here and I run again, and we'll have it in order traversal 20, 30, 40, 50, 60, 70, 80, and that is what we were expecting to get from that. So we are going to look at an implementation of this. Maybe like we'll build a product catalog search engine as our real world app that will illustrate how we use this tree. And let's say we have a requirement that the search engine must allow us to add new products by the product ID, to search whether the product exists, to list the product IDs in sorted order, and to remove discontinued products. So we will look at this in full in our live web conference, where we are going to build the product class and also build these different methods within the class that we can use to insert, to search, to delete. It's just like repeating what we have done here, but now we're going to be doing it as a real world app, and we're going to see how we can improve and optimize the operations of that tree by balancing the tree. In the next lesson, we're going to look at how we can balance a tree that is out of balance in a topic we call AVL tree. Thank you and see you in the next lesson.